Thanks, Elio. Thanks, Thomas, for organizing this wonderful meeting. I have learned so much already. It's been a wonderful couple of days. So great idea to do this. Yes, this talk will be dealing with issues of quantum criticality. And in particularly what we want to understand is the interplay between quantum criticality and superconductivity. And we will utilize also some technical tools that I find quite fascinating. The work itself was initially born out of wonderful collaboration with Ilya Esteles. Back then he was a graduate student at Stanford. He's now moved to the East Coast. A very talented graduate student, Gian Andrea Inkov in Karlsruhe, and a renowned scientist in the area of holography, Konrad Skalm, who wrote together with Jan Zahn, and as many of you know, a very important book on the subject. So superconductivity and quantum criticality is, of course, a problem that interests us in its specificity, in the specific relationship because we see so frequently superconducting order appear near, for example, quantum critical points in a number of systems. Related problems, of course, quantum criticality of superconductivity itself and how it might even be occurring in a critical metal. And an important question in this context, which I want to define why I find it important and relevant, is why is superconductivity in critical metals actually so abundant? Because it's a non-trivial question in some sharp theoretical sense. And then there's an even harder one, which I also want to address. No matter whether you do or do not have a quantum critical point, you could have a very, very poorly defined metal, a so-called bad metal, where typical scattering lengths of the order of the lattice constant. And you can still find that those objects are superconducting. To me, the by far most convincing and clearest examples are the cuprate superconductors here, showing some older data and newer data look more beautifully, but I think the substance hasn't changed, namely that we find a very broad spectrum in certain regions of momentum space, and others you don't, but in certain regions in momentum space, you find a very broad spectrum in angular reserved photoemission spectroscopy. And what changes in the superconducting state is a tiny but very clearly visible coherent weight. And how does this actually happen? Why is this legal procedure to do so? And this is, of course, something that has been seen in a number of different examples here. So show some data, I think, from the Brookhaven group. The Argonne group showed early on that these are really dispersing Bogoliubov quasi-particles that we are talking about here. So the wave function of that ground state of the superconductor seems to have some knowledge about the concept of the BCS wave function and Bogoliubov quasi-particles. And the reason why I think it's important to think about these tiny quasi-particle weights is because there's this nice phenomenology also around for a long time that you can correlate this weight of this coherent quasi-particle with, for example, this superfluid stiffness or the condensation energy. So not quantities that for a high temperature superconductor are quantities you should be ignoring. So now let's go back. So why is this an interesting question? And to understand this or to sharpen this discussion, it is very important maybe to reconcile one more time why, what actually is potentially allowed in such a quantum critical system. So let's look at the Cooper instability of a Fermi liquid type system with a self-energy that in leading order on the imaginary axis has a linear term. We sum up one of those particle-particle bubbles, the Cooper logarithm. So we perform the integrals, we see there's a logarithmic structure, the temperature is the natural lower cutoff, and we get an instability as we sum up this entire ladder. The implication is that superconductivity is the absolute natural ground state of a good metal. There are a lot more superconductors around than there are itinerant ferromagnets for just that reason. And it goes so far that Bardeen wrote a paper on explaining why sodium isn't superconducting. There's no paper around that explains why sodium is not a charge density wave, even though it could be due to the exact same interaction. And it's because we have this Cooper logarithm here that forces us in so many instances to simply go into a superconducting state. Now, if I now look at, say, a pure phenomenology, and we will have explicit calculations that give such behavior, but let's just assume for purely phenomenological reasons, an critical self-energy, so therefore a power law of the self-energy that is more singular than linear. And if I just do this, and this was done in the late and mid-90s by a number of very smart people, if you assume this and then sum up the exact same ladder, what you find is that the integral isn't divergent anymore, right? So this more singular behavior in the denominator makes it, well, better regulated as it's in the denominator, and hence you don't find a singularity. Physically, what it means is these are not really perfectly well-defined quasi-particles, so therefore their instability is weakened because they are more diffuse objects. The implication should be that superconductivity at quantum critical points then should be the exception, just like ferromagnetism in itinerant magnets, in itinerant systems is the exception, but not the rule. Now, there are, of course, some caveats in this argumentation here, and we will see this right away. So I know at least two clear answers why life is different than what we've just sketched there. And these are two very, very different interpretations, come from different communities, and I think have been motivated in a somewhat different way. But ultimately, we have here the superconductivity due to critical bosons has to be carefully evaluated. One can't just assume a self-energy of some sort somewhere and otherwise not change the theory, obviously. And the other one has something to do with our understanding of the deep connection between critical field theories and gravity theories in extra dimensions. And I will get to this in some detail. So the left-hand side here, so critical bosons, we have some bilinear of the fermions. It couples to some bosons. This could be a nematic fluctuation, a spin fluctuation, a phonon, that manages for some mysterious reason to become soft and continue to have this Yukawa coupling here. It could be a charge fluctuation. And if you work hard and are, then you get with reasonable argumentations power law behavior for self-energies. That is more singular than what we know from quantum criticality, from Fermi liquid behavior, just because it's at a critical point. There are open questions in this context, but to a reasonable approximation, if you're not too much of about all the details that have been evolving, particularly during the last 5 years, well, you could see, okay, maybe I get such a behavior. But what you get in addition in those theories is that not just the single particle self-energy gets singular, and therefore more diffusive, if you want so, the pairing interaction also gets singular. And more singular so than we would have expected. This exponent then has to be larger than a quarter in this context. So then this pairing energy is more singular than what we would have expected from the estimates that we've just made. And if you look at the power law here and the exponents, so this is of course a fermion inherited dynamics. Because it carries the same exponent, then you see it adds up in the exact same way to guarantee you an instability. I'll show you the equations. This is what I call the generalized Cooper instability. In my view, it was first clearly voiced by Abanov, Chubukov, and Finkelstein in 2001, but there is also a wonderful paper by Damsong on the superconductivity due to massless gluon exchange in color superconductivity, and a number of follow-up works that is wonderful and goes along very similar lines. This is statement number one. Statement is the pairing interaction is more singular, hence we cannot avoid superconductivity even though we have lousy quasi-particles. The second statement is a very different one in philosophically and technically on so many levels. So what you're saying is, I know how to, I exploit a duality, which I give you a couple more details on the next slide. I exploit a duality between field theories in d+1 dimension and gravity theories in one extra dimension, which is sketched here. And that this duality generates me power laws. And then I'm adding basically a Ginzburg-Landau type theory in this curved space, and check what happens. Now, when I saw this for the first time, I thought, well, what's the big deal? The big deal is that if you find natural solutions in this gravitational setting, then you almost, which means for critical systems, then you're almost guaranteed to have superconductivity in such systems that are critical. This is, in a way, this says Cooper pairs can form in those critical systems rather naturally. This goes back to the late Steve Gubser and to Hartnell, Herzog, and Horowitz in 2008. Now, in both cases, you can, of course, voice objections, right? On the one hand, I mentioned already, is this really allowed, controlled? Aren't there problems? Is this really all kosher? And those are very, very valid objections. And to some extent, some orthogonal objections you can voice for the holographic description, which means, is this really relevant? And isn't this an artificial oversimplification? And does chemistry really care about conformal invariance and so forth? And so, and the fact that these are to some extent orthogonal objections makes me optimistic, because what I want to show you is that they're actually very, very closely related, much more closely related than we would ever have thought. At least I had thought. I'm sure there are others who had a better understanding. Now let's comment a bit more on this holographic story. It goes back to the late 80s, when incredibly smart people realized that there's a deep connection between certain quantum field theories and gravity theories in one extra dimension. So what we're doing is we're looking at a quantum field theory that had time and space somewhere, and we look at it from the side, so we can add an extra dimension, and this extra dimension is curved. There can be at finer temperatures a black hole sitting here. And the scale here has much to do with what we know in condensed matter physics to be the renormalization group scale, but this is the UV behavior, and we flow into the IR behavior, and that's what we at low energies are interested in. So our theories flow and undergo renormalization group flow, and there's some true and explicit aspects of this that you can understand it, interpret this way. And one more time, this interesting statement from Gubser, Hartnell, Herzog, and Horowitz was that you can actually spontaneously break a symmetry near such a black hole. Insofar, this was at least initially not so obvious, because there's, at least for non-anti-de Sitter spaces, so I should maybe point out this gravity is lifted in so-called anti-de Sitter space, meaning it has a negative cosmological constant. This is important because that allows you to give a thermodynamically stable state. I mean, if in flat space, these black holes evaporate, as we all know. So this gives me a positive heat capacity. So, so this theory gives us, has permission to have spontaneous symmetry breaking, which is an important statement. And you can draw conclusions, for example, that charging the system in an appropriate way actually enhances pairing. But also you need to keep in mind that just changing the sign of the quadratic coefficient ain't going to be enough, because the gravity or the curvature of the space doesn't like really to this condensation, and there is a bound. So you need to be more negative than a certain number that was worked out by Brighton, Lohner, and Friedman long ago. So this is the description of this critical theory, and we will get back to this as we move on. But now we need to talk about explicit condensed matter models, if you wish so. And the model that I want to present is a derivative of another one that was discussed in the early 90s, 2000s, and then more recently by Kitaev in 2015, the so-called Sachev-Kitaev model. A very, very simple but incredibly telling model, where we have fermions that have an interaction where every site interacts with everybody else in any possible combination. And these are random interactions, ultimately giving rise to suppressing all kinds of alternative orders and lifting degeneracies in a very, very clever way. So now you solve these problems, and that's the beauty of it. It's a fully connected problem, so it's not overly surprising to us that this can be solved. But you solve it in the way that you introduce replicas, average, and introduce bilocal fields. So you basically have a theory where the natural variables are Green's function and self-energies, as opposed to fields. And you can write down the action, which is incredibly similar to what we've seen earlier in a number of talks, these large Luttinger-Ward type functionals. But they are basically entering here as an action. And I believe dynamical mean field theory must be formulatable. I haven't seen it in all its glory, maybe worked out, but must be formulatable in just the exact same way, that you understand it as a theory of fluctuating particle correlations with bilocal fields. And then you get a saddle point, which gives you then the dynamical mean field equation. And in this case here, equations are basically the Dyson equation and what amounts to just a self-consistent second-order perturbation theory. Of course, that's not what you do because there's no perturbation theory concept, because all there is interaction, but it looks mathematically just like that. Now, if you assume and later confirm that this self-energy is more singular than the derivative here, you can drop it. You can solve it in a couple of lines. Was done in these early works here in beautiful fashion, and Georges and Pacolet generalized it to finite temperatures. And you find these power law behaviors that translate into just the same power law behaviors that I gave you for the single particle self-energy early on, and the exponent then takes a value, in this specific case, 1/4. So we have a tool here that gives us a non-thermal liquid, a critical non-thermal liquid for free. We don't need to work hard to get that. Before I want to look at superconductivity in a related model, we need to learn a little bit more about the fluctuations of this problem. And so first of all, this is a spectral function just to give us an image of what these incoherent objects are. So that's a sharp peak, but still it is not an arbitrarily sharp peak, but it's a power law structure. And it has an interesting property, namely that in the solution I pointed out to you, you can actually change the time by any function of time. And if you stay in this low energy regime, you find that it's still a solution. So actually you find an infinity of solutions that are all solving those exact same equations with the derivative here cut off. So you have a large number of solutions and it looks like a soft mode. But of course, if you do this numerically, you wouldn't notice because the UV physics, so the high energy physics, fixes one out of those many solutions. And you can do this by including those time derivative as a small perturbation. And if you basically do this, you find that the fluctuation spectrum can be written in terms of these fluctuating, but now energy costing contributions. And there's some funny action that has something to do with the underlying conformal field theory, so-called Schwarzian action. And then you have all the other stuff that I eloquently called other fluctuations. So those are basically these soft modes, and then you have other potential fluctuations. And now comes the connection to gravity and becomes much more clear and maybe explicit, because this is a system that lives in one time dimension. It's a zero-dimensional problem, so it should map onto a two-dimensional gravity theory. Two-dimensional gravity theory is trivial or not even really existent, but you can find versions of it where you basically project from higher dimensional onto two-dimensional subspaces, and that is the so-called nearly anti-de Sitter space 2, ADS2. And this has an action that is precisely the same one that we've just seen here from the Zatshev-Kitaev model. What it means is there's some geometric similarity. This is the leftover of the Einstein-Hilbert gravity action here, and this is what we see for the Kitaev model. It is not clear that therefore these models are in any way more directly related, but there is this connection for sure, and what one needs to see is whether other fluctuations indeed also have that property. So we want to look at superconductivity, as I pointed out, and in the Zatshev-Kitaev model, there were a number of works that dealt with this problem, and our approach was to look at the exchange via bosons, and it was, again, this work here with Ilya and Daniel Haug and Markus Klug and Ilya Esseles and the follow-up work. But there's closely related work from Yushan Wang, from Debanjan and Eres, and there was an earlier work that assumed an instantaneous unrenormalized pairing interaction is a problem by Una Kim and Avishpa Patel and Mass Lawyer. So this is, so there was some development in this area. I want to discuss this specific work here with Ilya. This is our model. So we have Now, fermions that interact with bosons, you can call phi a phonon or a charge fluctuations, and I'll give you an example when it could be a spin fluctuation, and these bosons have their own masses and conjugate momenta. And this coupling constant is now this disordered object that we use to generate a sufficiently frustrated and sufficiently critical system. So there is a bit of mass here, and the only important thing is that you need to think, you need to think a little bit on how the disordered distribution of this object can be chosen. And there's a parameter, I call it alpha, that interpolates between certain different disorder configurations. Why is this important? Because you can have disorder configurations that do or do not break time reversal symmetry. And one is poisoned for the superconductivity, so you don't ever get superconductivity, and the other one isn't. And therefore, we can actually switch in the system if you want. So we can do pair breaking impurities, mix them into this disordered configurations to tune off and on the superconductivity, which is a wonderful knob for the theorist, and which is essentially the Abrikosov-Gorkov version of quantum critical theory superconductivity. If you wanted to look at spin fluctuations, you can do the same. You could, for example, do some Fermi surface with hot spots, and you can patch them in some appropriate way. And then the boson would be a spin, as you can see here. And the boson is missing. There should be a boson operator here. And otherwise, you have very much the same mass, and it's not particularly different from the problem that I wish to discuss right now. So the technique has been set. What we need to do is to do disorder averaging and introduce these funny bilocal fields. Again, this is philosophically very close to dynamic mean field theory. And in addition to bosonic fields now and our fermionic Green's function, what we get is, of course, anomalous energy Green's functions and self-energies. And those are fluctuating dynamical degrees of freedom. That's how we have to look at them. And at the large n limit, there's an n up front here in the exponent, we get equations that are mathematically identical to the good old-fashioned Lerchbeck equation for superconductivity. And the phonon, if you want, or the boson, drives the superconductivity. It becomes a critical object. The fermions become critical by themselves, and this soup of critical degrees of freedom then does or does not undergo superconductivity. It gives us at least a glimpse at what can happen in a controlled theory, albeit very artificial, to critical superconductivity. The normal state solution has a phase diagram. It's a bit richer than the SYK model originally, and the reason is because we have in the model the phonons have a bare mass, and therefore I can construct an additional dimensionless coupling constant out of coupling of this interaction here and this mass, and can tune it. So there is, if you want, so a weak and a strong coupling limit, but of course you're always in the strong coupling limit if you compare to the kinetic energy, because you have set it to 0. So there are different versions of strong coupling if you wish so. At lowest temperature, we find something very similar to the purely electronic SYK model, and at higher temperatures, that regime can down to t = 0 and the dimensionless coupling constant infinity limit, we find something that is even more incoherent. So let's look at these solutions. So we are prepared then to look at superconductivity. Yes, indeed, we find those power laws, and the exponents earlier were chosen to be exactly the same ones. And what we find for a certain set of parameters for a certain formulation of the theory is some exponent between 1/4 and 1/2, and one can tune this if you want so. So there's these power law propagators, and Landau damping dominates the boson and gives its own completely singular structure. And these two are again governed by the exact same exponent. One gets fractional Landau damping in the system and so forth. So that's this low temperature regime here. And then there's a high temperature regime that is somewhat different in character. Here the electrons are completely and utterly incoherent. There's no structure left. The reason is that these bosons are getting so soft. The energy gets so low that they look like classical impurity to us. And then, well, this is just, the self-energy is just the one-off classical impurities. And you get this soup of, say, almost classical degrees of freedom, but the system is still non-trivial because it actually becomes superconducting, which, if this was a purely classical problem on its own right, of course, wouldn't happen. Superconductivity is everywhere in this phase diagram. We know how it behaves as a function of coupling constant. It's different, of course, from BCS theory. There's no reason why it should be even resembling it, but you find it everywhere for any coupling constant. That's this generalized Cooper instability. It would be in its nature S-wave, of course, if these are charge fluctuations of phonons, and if we use this patch construction, it would the natural solution you find is, of course, as you would expect, a D-wave solution. For strong coupling, these transition temperature saturates at a value in the units of the bosonic energy. And you can look at the phase diagram basically like this, that there's one regime where basically superconductivity sets in instead of the critical behavior. So superconductivity just prevents the system from being so nastily critical. And you also have a regime where you're deep in this incoherent soup of completely ill-defined carriers, and you still undergo a transition to a superconducting state. So now, and this is where we know we make the first connection to one of my two answers to the earlier challenge, namely the critical boson theory. If you look at the linearized gap equation, so I told you, it's just the Lerchbeck theory. So I can write down the Lerchbeck theory, but it's the Lerchbeck theory of critical bosons. And the linearized version is maybe most telling. And it has a structure where we have here the singular boson interaction, and here our fermionic self-energy. And you see this would not be alone sufficient unless if you introduce at least the tiniest amount of kinetic energy to drive an instability. And this term here compensates. These powers add up exactly to 1 and give you a pseudo logarithm. And that's why you keep getting these Cooper instabilities. Now I like this formula because the exact same gap equation, I mean precisely just different values for the exponent, occur in theories as diverse as the ones I'm listing here: antiferromagnetic and ferromagnetic spin fluctuations in 2 dimensions, gauge field induced composite fermion pairing, pneumatic fluctuations, spin liquids, and quark gluon plasma or at low temperature. So when you have color superconductivity, and here are some of the references. This equation was also recently investigated in a series of wonderful papers here by Abanov and Chubukov and collaborators in this context. This is the boson exchange superconductivity of critical bosons, and we get that here as well. At strong coupling, where the pairing saturates, it's basically even though you have completely incoherent fermions, they don't really bother you for the mathematically same reason as Anderson's theorem doesn't destroy impurities, don't destroy superconductivity in disordered systems, and there are leftover quantum fluctuations that can still give rise to superconductivity, and that's why you get it here. Curiously, there was a Monte Carlo analysis of an electron boson version in real lattices that also found a bound for TC of the order of 0.1 than the typical bosonic energy, and this is accidentally probably very much the same, but there seems to be some issue of saturation in these system. How strong you making the coupling constant is not important. This strong coupling regime has quite curious spectral behavior. In the superconducting state, you find a tiny Bogoliubov quasi-particle weight that vanishes in the coupling constant and actually goes to 0 in the extreme strong coupling limit, and you find these very curious shake-up peaks that to some extent you should consider that this is not an ideal gas of Cooper pairs, but the Cooper pairs are strongly interacting objects and form themselves funny bound state behavior, something that was also seen in extremely strongly coupled electron phonon systems by Combeseau a number of years ago. We used this very strong coupling version of the theory to look at something that was mentioned yesterday in Piers Coleman's talk, namely to understand what was mentioned to be dark fermions, where photoemission spectra, here by Adam Kaminsky and Takeshi Kondo, were analyzed by a group of Imada, and they could distill from it in a clever way anomalous self-energies that are singular at low frequencies. This is the green curve and the black curve, where the total self-energy. It's a problem that I would give the system that, of course, composed of those two objects that are fluctuating in the SYK theory. This object is very regular, the red curve, but there is some intrinsic singularity in these two curves that cancels. And we use the SYK type dynamics, and in the strong coupling regime, you can very naturally understand it. It is the singular, strongly retarded pairing interaction that gives you this behavior quite naturally as well. Finally, maybe we got under the coherence, the quasi-particle coherent weight in its smallness naturally also explained why condensation energies go down. As I mentioned, this is something that was seen in a number of experiments. So it is maybe also played on purely phenomenological level, not overly surprising if you have a small weight, that then the superconductor really has a small condensation energy. The fact that they truly scale with one another is at least a non-trivial statement that follows from this little toy model as well. Good. So we have now an understanding of a critical superconductor. And it's always interesting, and as it appeared everywhere in the phase diagram, we were particularly interested in ruining that superconductor, because you always want to know what is it most susceptible to, how can you destroy it, and how does it behave when you do so. And that's why we introduced pair breaking, as I mentioned earlier in a work last year with these courses. So we introduced pair breaking, and clearly these low carrier, these low quasi-particle weight state here is, even for tiniest amount of pair breaking, very, very fragile. While the quantum critical state is initially modestly fragile, but what's most important is there is, independent on any coupling constant, a critical value for the pair breaking where the superconductivity disappeared, and it disappears in a very funny way. It disappears with this essential singularity that we know, of course, from the onset of correlations in the Kosterlitz-Thouless transition, where, of course, this here is driven by temperature. Now, it turns out that such behavior is indeed something that was also obtained in those holographic problems models in entire zeta space 2, the one that would be the natural candidate for us to look for a holographic dual. So again, so this behavior that you have an essential singularity and not critical exponents governing this quantum phase transition here is something that very generally happens when you break spontaneously a conformal symmetry, which you of course do. The critical state has some conformal symmetry, and the superconducting state breaks that symmetry, opens up a gap, gives us a fully gapped ground state in the system. Maybe if you're curious about nice formulas, so the anomalous self-energy at that point here, it's this critical point, has this beautiful power law behavior that can be found quite nicely. But we had just earlier discussion about multiple solutions of Luttinger-Ward functionals. We find at this point an infinity of multiple solutions, but only at this point. Otherwise, they're separated by an excitation gap, which is on its own right very interesting. Now, with all of this, we have now gotten an understanding that we have a tool that gives us superconductivity in critical fluctuations. And as I told you, in that SYK model, we already knew that the gravity part, if you want, so the version of the Einstein-Hilbert action that gives us the Einstein equations of that gravity theory, is already taken care of. It is a result of the UV perturbed conformal theory of that critical state, which is natural for the description of this entire zeta space. But then there were these other fluctuations, which I don't think have been clearly understood in the same context. And we, of course, now have a theory. We have a fluctuating superconducting bilocal field. Our anomalous free energy, and we can obtain from our SYK superconductor, of course, its own action. We can perturb around the normal state, which is the easiest thing to do, and we can then get an effective action for an effective theory for this fluctuating superconductor. It's a bilocal field, that's important here. So what it's most natural to do, of course, takes these two times. Of course, on the saddle point, it only depends on the difference between these two times. But fluctuation configurations clearly do not have to have that property. So you Fourier transform with respect to relative and absolute time, and I use the variables epsilon and omega here. And therefore, I have a variable that depends on two variables, a quantity that depends on two variables, not just on one in the theory. And again, using our normal state results, we can just at least look at the Gaussian contributions. There are two contributions. One is basically particle-particle propagator of a non-Fermi liquid state. And among others, it will dislike pairing for the exact same reason that I showed you on my second slide, because the Cooper instability is weakened by this term here. And there's another term here, which is more wonderfully transparent now, fluctuating and retarded singular pairing interaction governed by the very same exponent. And it's the fight between these two terms that has to eventually decide what is happening in the system. So this is the low energy action of the superconductor that fluctuates around a critical normal state. Now,
4 minutes plus questions.
Of course.
4 minutes plus questions.
What did you say? Sorry.
4 minutes plus questions.
Oh, wonderful. So what we did is I can of course take the saddle point of this equation, then I recover my Leerstück equation back. But you can do something else. It gives us some additional insights. I introduce a very funny field at the first glance. I take my my fluctuating propagator, my Gorkov propagator, I do a Wick rotation with respect to the total time, Fourier transform with respect to the relative time, and call that frequency 1 over zeta, and introduce an object psi of zeta and t. And then it turns out that this field in this formulation, the action I just gave you, is nothing else but the holographic superconductivity in the gravity problem that is made up of an anti-de Sitter space 2 in the appropriate so-called Poincare coordinates of the system. So you obtain gravity and geometry out of that formulation of the critical fluctuations around the critical normal state. Often in holography, what you're doing is you're starting from you're using the duality as a concept, and you're starting making the assumption that it's valid and starts from a gravity theory. What we've done here is we went the other way around. We started from the quantum mechanical many-body theory, and you show it is a gravity theory. A few implications. Well, our singular pairing interaction gives us a negative mass. That's good news. The charging the system will always drive the system towards higher TCs, which is something that Stephen Gooks already pointed out early on, but we know can translate this gauge charge into the deviation from half filling explicitly. Finally, the tendency not wanting to order is purely geometrically hidden in the problem in the mentioned Brighton-Lohner-Friedman bound, so that the mass has to be more negative than a certain number. So this suppression of Cooper instability is hidden in the geometry of the underlying system. My last slide. So this is how we have to look at this. We have time going this way. This is the absolute time. And the second dimension is essentially inverse frequency of the relative coordinate. That's the RG coordinate. At finer temperatures, you find there's a black hole forming at the temperature. The temperature then acts as a lower cutoff in the problem. The saddle point equation is the Leerstück equation, and we know that at least near these critical points, indeed, we can find a differential equation, versions of the saddle point equations, and they are actually identical to the Schrödinger equation of this particle in this anti-de Sitter space. For future work, it's particularly interesting because we have this axis. We can now easily, and much easier than on the field theory side, solve non-equilibrium dynamical problems, look at the dynamical susceptibility and so on. And I've just gotten an hour ago from John some first results on this one that are extremely promising. So we have another tool to understand the non-equilibrium dynamics of the system. So we have a model, a toy model, admittedly, that says something interesting about critical pairing. It is on the one hand gives us equations that are identical to the ones that in a large class of condensed matter systems have been obtained. But on the other hand, given its simplicity and clarity, we could derive from it the action of a holographic superconductor, which makes me to believe that these are actually the same theories, at least conceptually in the sense of universality classes. Thank you so much for your attention.